Hey everyone, thanks for jumping on. I wanted to take a few minutes to walk you through this AI infrastructure calculator I put together. Honestly, the biggest trap I see that engineering and product team falls into right now is like looking at a new project and immediately jumping, assuming that they need to spin up a massive, incredibly expensive frontier model to get the job done. But as we know, throwing a massive frontier model at a straightforward task is just huge waste of budget if a smaller fine-tuned model can do the exact same job for the fraction of the cost. So my goal with this design was to make it easy to right size your hardware to the actual task. So instead of dumping a massive list of 50 random models in your face, I split the interface cleanly into LLMs and SLMs. Watch what happen when I select a smaller model, that is SLM. The entire provider model and model list instantly updates. We can pivot on the fly to lightweight text model like vision models. Okay, like say vision model, text model, or even dedicated voice model like Whisper. Okay, so so you will notice the entire UI switches instantly behind the scene without breaking your active configuration or dropping the app in state. For a walkthrough today, though, let's look at the absolute go-to for enterprise application right now. The Llama, let's say Llama 3.3 billion, that is 3.3, which is a 70 billion parameter running on FP16. Okay, that is the precision. Okay, let's select. Okay, I'll select floating point 16. Okay, as a precision. Okay, so so now a ton, like let's say so it's a ton of teams are spinning this up because it's a perfect baseline to show you where your hidden infrastructure costs are going to spike. All right, so let's walk about let's talk about workload profile, because this is where the real surprise happen. Most people thinks running a 70 billion parameter model at a floating point 16 just takes a flat 140 gigs of VRAM. But watch what happens when I simulate a real world enterprise workload. Let's ramp up our concurrent user up to 30, and max context window to 16,000. Okay, so 16,000, let's say 16,000 token, that's it. It's a long document that we have taken. Suddenly if you see our total VRAM, okay, the total VRAM requirement leads up to 200 gigs of memory. Okay, 200 plus gigs of memory. So look at the stack bar. This the blue block represent our model weight that stays completely frozen, but the purple block, okay, But the purple block right above it, that's the KV cache, and it grows aggressively with every single user and token you add to the system. So, oh yeah. By the way, look closely at the math here. Okay. So we are sizing this based on KV heads, not full attention heads, which accurately captures the group query attention efficiency built into modern architecture like we have a llama. Okay, so like llama. So if you don't calculate that specific cache footprint accurately before you deploy, your application is going to hit an out of memory wall the second it sees peak production hours traffic. Okay, so if you go back go down, okay, yeah, this line chart below shows you exactly where that danger zone is. The precise interaction where your memory cache officially become a bigger cost driver than the model itself. Okay, now let's talk about what if scenario. So in the real world, traffic isn't static. Okay, traffic isn't static. Scale happens quite fast, which is why I built this what if scenario matrix right into the center tab. Okay, think of this as an instant stress test for our infrastructure strategy. Okay, it takes our baseline profile and automatically run the math on unexpected spikes. Okay, so like what happened if our user base suddenly doubles, or our document size doubles, or if both hit us at the exact same time. Instead of forcing you to recalculate everything manually on the whiteboard, it cross references the spike against our hardware allocation and flags a blunt green, or you can say blunt yes, or saying a upgrade is needed. Okay, it gives you instant visibility into our true scaling runway. Now let's talk about RAG. Okay, so almost every enterprise app needs to ground its model with a proprietary internal data. But a common mistake is forgetting that our embedding and vector database indexes don't live on your expensive GPUs. They live in a memory on your application or a database node. So if I flip the enable, let's take an example. If I flip the this particular thing, okay, watch this. Okay, so let's choose a standard embedding model. Okay, let's say text embedding 3 large, and let's say index is around let's say 5,000 50,000. Okay, yeah. First, let me check here. Okay. Okay, so now if you see, the app breaks down the total vector count and explicitly factors in a 35% memory overhead for an let's say for an HNSW index. Okay, so which you need for fast similarity search. And look at the bottom. Okay, it hands you an explicitly infrastructure recommendation. Okay, recommendation. Here it tells us the database takes up less than like 16 gigs of memory. So it can sit comfortably on a standard low cost server node without needing a complex distributed cluster. Fit into real world silicon. Okay, and that brings us to the GPU landscape tab. So I built this interactive chart to give us a bird eye view of the entire enterprise market. We are plotting a memory capacity on a bottom against raw compute speed on the side. Okay, and the size of each bubble shows you the actual cost of the card. Look at the spread here. You can see the next gen heavy hitter like NVIDIA Blackwell 200 as or AMD MI 350 MI 350X, okay, sitting at the top right. But look down here, okay, down at the chart, okay. So uh, like you can see the L40X and the RTX series like 6000 gives you a massive cost efficiency if your model doesn't need insane compute bandwidth. Okay, and right below the chart, the app takes you our exact workload and output a ranked leaderboard of the top 4 hardware configuration. That makes sense for our budget along with a clear justification of why we picked them. Okay. Now, finally, the best part that I like the most is the money. Let's talk about the money. Okay. So, if we click over to the TCO comparison, okay, that is total cost of ownership. Okay, tab. So we'll get a multi-year financial projection comparing a third-party cloud API, 24/7 cloud GPU rental, and an on-premise deployment. And just to be clear, the on-premise one, okay, on-premise calculation isn't just looking at the retail price of the hardware. It accounts for real-world operational realities, electricity cost per kilowatt hour, a 1.5 cooling efficiency factor, and annual maintenance percentage, rack space, and let's say engineering labor overhead. So if we circle all the way back to the main executive summary, okay. So okay, yeah. So the complete application strings, all of this engineering data and financial analysis into a single cohesive briefing. It justify exactly um, why it is recommended our specific hardware configuration, call out our precise scaling limit, and finishes with a list of vendor red flags. Okay, these are highly specific, pointed out questions you can copy paste directly into an email to grill any vendor or cloud provider trying to pitch you on a AI infrastructure contract. And this is the walkthrough. It bridged the gap between deep transformer math and the bottom line business financials. I would love to hear your thoughts to dive into any specific section. Yeah, one more thing that I want to add. Sorry, is a display. You can change the currencies as well according to, let's say, INR, CHF, or USD. Let's say INR. So the complete calculation changes according to that, according to the market. Thank you. Bye bye. Now, now once you know your VRAM and your database footprint, you have to actually map